Hello, welcome. As you can see, this presentation deals with polygonal fractures in the Navajo sandstone of southern Utah. I'm Dave Loope. Kara Burberry, Clint Rowe, and I are with the UNL Department of Earth and Atmospheric Science. Garrison Loop is with University of Arizona Geosciences, and Jerry Bryant is with Dixie State in St. George, Utah. The Navajo is a Jurassic Aeolian sandstone that's over 1,000 feet thick over most of the study area. The study area is within the Colorado Plateau, shown here with the red, and the Basin and Range Province lies out to the west. We've got two sites out there. The 5 black circles are near our study sites. Here are those polygonal fractures. They occupy the sloping surface of a Navajo crossbed set. The skinny arrows show where water has flowed over the rock, and here you can see that some of the fractures have been erased along the watercourses. That shows you that the fractures are shallow. They're usually less than 15 centimeters deep. They are on the rock, not in the rock. Here's a map showing a portion of the polygonal pattern at that site at Yellow Knolls. If you exclude the blue composite, which are produced by erosional scour, the red hexagons are by far the most abundant type. They're about twice as abundant as the 5-sided and the 7-sided polygons. Basaltic lava flows commonly display polygonal patterns. One of the most famous of these lava flow sites is at Giant's Causeway in Northern Ireland. You can see here for Giant's Causeway, the polygons there are also dominated by hexagons and lesser portions of 5 and 7-sided polygons. Here's a close-up taken at Giant's Causeway. This is basalt. These fractures formed after the lava had solidified into brittle rock. As the rock cooled further beyond that, it fractured. Note that there's Y-shaped fracture junctions. Contractile stress is what opened these fractures. The temperature difference at the same time within the same solid rock. That's where the stress comes from, and in this case the thermal stress was sufficient to break the rock. So contractile stress was also what opened the fractures in the sandstone. Notice that these are also Y-shaped, but also keep in mind that sandstone, especially the Navajo sandstone, is much weaker than basalt, so less stress is required to open the fractures, and so probably less thermal difference between cool surface and warmer innards. Here's what happens when mud dries. It generates polygons, but note that the junctions are different. These are T junctions, and there's multiple generations. The first cracks to form relieved about half of the total stress, and the rest of the stress was relieved by these that are perpendicular to the original first generation. So these T junctions are really distinctive. The process of multiple generations of fractures on the same surface makes this distinct from the basalt flows. So more about basalt here. So here's Giant's Causeway again, but that's just a cross section. Here you see the full breadth of the hexagonal fracture pattern. So these are elongate columns. That's definitely not present in the sandstones. Remember, the fractures in the sandstones were only 15 centimeters deep. Also notice that at the top of the lava here, there aren't any columns. So columnar jointing apparently starts in here and proceeds downward. This is a diagram published in 1988 by Aden and DeGraff, and they were the first to realize that the hexagonal patterns like you see at in Northern Ireland evolves. It starts out as as T junctions, a 90-degree junction here, and evolves toward Y junctions. So this is where the columnar basalt starts. Up here in the uppermost part of the flow, you don't have the hexagons, but then you do get this hexagonal pattern. So is this at all similar to what goes on in sandstone? Do the sandstone fractures somehow evolve with depth? Well, we think they do evolve, but not with depth, but with time. So if we're interested in thermal fracturing, we need to get some data from drilling holes into the sandstone and putting thermistors in there along with the data logger. So in the remainder of this presentation, I'm going to tell you why we think the hexagonal pattern in the sandstone, like that in basalt, evolved, but it evolved through time. And in the case of the sandstone, it took much, much more time than in the basalt. So in this case, there's the shallow sensor, there's the deeper one, 2 centimeters and 15 centimeters down. The blue line here is the record of temperature shifts during daily cycles. So here you see it's mid-August, and the high temperature here, 45 degrees Celsius, probably at 2 p.m. or so, and then the coolest part of the night just before dawn, that's 25 degrees C cooler than what you had in the middle of the day. This lower curve is showing you the temperature difference at any one time for the difference between the shallow and the deep sensor. And so that's what generates the stress, the two different temperatures at the same time. So here you can see that the stress generated in the middle of the day is much greater than the stress generated in the night. So remember, it's contraction is what we need to open these fractures. Compression doesn't do us any good in terms of generating these fractures. Contraction is what we need, and these stresses are not very great. What about wintertime? Maybe contraction is greater than in summer. No, they're weaker than in summer. So here the difference is almost right at zero. And the greatest differences are in this part of November when you had hot days. So this is somewhat similar to the summer pattern. So clear days can get really hot, clear nights can get cold, but we're not getting it done yet. There's another possibility. In August on the Colorado Plateau and in the Basin and Range, there's a phenomenon known as the Arizona monsoon. And so most of the rain that falls year-round is coming in August. Here we've got a record of thermal stress. This is the difference between the rock temperature at the two different levels in the rock. In the middle of the day, it gets pretty high. In the evening, the temperature drops a lot. But here again, this is not much stress. But take a look. 1, 2, 3, 4 cases where the stress spikes and is more than double the typical stress generated in the cool nights. So this is the stress generated by rainfall. The largest spike was a rainstorm. It only delivered 12 millimeters, 1/2 an inch of rain, but it really cooled the surface down and generated a big difference in the temperature of the two. So this, we think, is the best way to generate contractile stress it's not only greater stress, it's also being applied much more rapidly. So the hexagons in the rock evolve with depth, and it's iterative cracking that is believed to be the key to the formation of hexagons. The first cracks, we don't have that pattern, but more and more cracking is taking place as the lava cools, and eventually you get shifting of those junctions from T's into Y's. I didn't tell you, but in the Navajo sandstone, this kind of fracture pattern is also common. It's probably more common than the hexagons. This pattern is common on very steep slopes, and these steep slopes are unstable. So you can see blocks of rock here that have fallen away. There's rock slides and rock falls. So I'm getting at the point that maybe these don't have enough time at the rock surface to evolve the hexagonal pattern. Here's a lower slope, and it looks like there are both the rectilinear, the right angle junctions displayed here and here. The T's are tectonic joints, not superficial fractures, but through-going fractures. And in between, there's some fractures that are somewhat parallel to them, but these are superficial. All the fractures except the two T's are superficial fractures, and you can see that although there are T's here, there are Y's here and here, this zigzagging pattern. So we think that this is the intermediate that helps to demonstrate that, like the hexagons that form in basalt, it's iterative fracturing that's taking place near the land surface in this case, and it's leading to the formation of hexagonal patterns. Here you see a fracture. We think it started out as a straight line that was met by other perpendicular fractures, shown here in dashed, and with time and repeated fracturing, this evolved, and then these curves developed in further evolution of this crack pattern. So we've got the precursors, we've got something to work with. The fractures on the steep cliffs and slopes are about the right size, and what happens through time, if the slope is relatively shallow, the rock is removed by erosional forces, and here you see all this rock eventually is gonna get fractured as erosion proceeds. The slope is, sand is removed from the slope, and the rain continues to fall, the cracking continues to take place, so maybe depth isn't needed, just time for this erosion to play a role. It plays no role in the evolution of the hexagons in basalt, but the key thing is iterative cracking. And here you've got cracking, 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 and it's happening maybe on a yearly basis, and it may take thousands of years to develop the patterns that we see. So our main conclusion to this question, do sandstone polygons evolve like those in basalt? Our main conclusion, which is new to science, is yes, they do evolve, and the only difference is it's time, not depth, and erosion and iterative cracking are required. So here are some other conclusions that emphasize that the similarity with basalt and sandstone is based on a steadily moving cooling front. So in basalt, it moves pretty fast as the really hot lava cools down. In the case of the sandstone, the cooling is moving very slow,